Well, thanks for coming, everybody. Today, we are going to focus on common reward games and value function methods. And the reason why we're looking at these is because these are a particular subset of multi-agent reinforcement learning tasks, which effectively can be reduced to a single agent problem because there is a common reward signal. And what makes a lot of multi-agent problems challenging is when you have agents with their each having their own reward signal, and you have to figure out equilibrium solutions, and it's not as straightforward as just trying to maximize the reward. In common reward games, we are just trying to maximize the reward, but here the challenge is really now just dealing with the joint action space and how large that can be when you have a lot of agents. So it really is a subset of problems where the value function itself is sufficient, usually, to solve the task, just like, value function methods work in ordinary reinforcement learning. And we saw that with other types of games, sometimes the value function is not sufficient to even compute a solution. Here, that is not going to be the problem. The problem instead is going to be that evaluating a value function over the whole joint action space may be too. Oh, David, you have a question? Sorry, I'm just going to mute you if that's okay. So that with a large joint action space, it can be sort of intractable to actually have a function that operates over this whole thing. And there are different approaches to dealing with that. One of which is to decompose the value function somehow, factorize it. So we're going to look at a few different approaches to that. So if we go back to the game models we had started with at the beginning of the book, we have, we've been looking mostly at stochastic games where we have different game states and then n agents. And here we're just looking at this common reward subset where, earlier we had looked a lot at some zero-sum games. These are games where the sum of rewards across all the agents is always zero. Now, another simplification, but these types of games are not reducible to single agent problems because they are fundamentally about how the agents compete against each other. And then in general, some games we have a reward signal that could be any value assigned to each agent at every step. And this will subsume both of these categories, right? Because a general sum game could also be a zero-sum game. It could also be a common reward game if the reward assigned to each agent just happens to be the same value in all states. But for the common reward game, there is just this single reward value. So also I'm just showing here some of the code I have written so far for multi-agent learning. And this was code for the first part of the book where we dealt with tabular problems. So we can represent like the transition functions more directly with these sort of lookup tables that are maps across all of the states. But here, I had defined sort of these different subtypes for common reward games and zero-sum games, because for both of these types of games, you can represent the whole reward as just a single value. So like for zero-sum games, at least ones with two players, right, we can just say what the reward is for player one, and the reward for player two will always be the negative value of that. And for common reward games, all the agents share a reward, so, we also just need a single value for that. I can show another. Actually, let me see what I want to show here for this. Yeah, so this was one of the examples we're going to look at. What we have been looking at in this chapter, this level-based foraging task, which is effectively just a grid world problem where the agents move in a grid world. And this is a tabular version of the problem where we can see exactly what it looks like. But this is a general sum game, a general sum stochastic game. So you can see here in the reward transition map, I mean, the rewards in this game are sparse, so you're going to see most of these values are 0. But there are 2 values in each, for each sort of state action pair, state joint action pair here, which is the reward assigned to each agent. And in a common reward game, this would just be a single value. And also, like, these slices of this is representing the transition function across all of the states in the problem. So here there's like some 57,000 states, and then each agent has 6 actions. So this is showing the transitions across this 6x6 action space. And if we look at a solution to the problem, like, this is one of the techniques where we learned joint action values. For general sum games, you have to do something with the joint action values. It's not as simple as just learning them. But for a common reward game, just learning these joint action values is enough to come up with the optimal policy. We can see here also this value function is over the same type of dimensional space where we have all the states in the problem and then this 6x6 joint action space that we're trying to learn. So when an agent has learned this function and it's like the optimal value function, then, if you have access to this centralized value function, which is not always true because sometimes, the agents only have access to a subset of the information. But if we have this centralized value function, then the optimal action for both agents would just be a matter of selecting which of these joint action values is the highest value. So like in these states, if they're all 0, it's just the policy is indifferent to the actions. But so maximizing this across the joint action space is the same thing that we would do in ordinary reinforcement learning, but we wouldn't call it a joint action space because we would have already taken that and turned it into just a normal action space. But in that case, each action would be representing one of these joint actions across both of the agents. And that's what we did when we looked at central learning reductions to the problem. So I think it was in, let's see, was it in this notebook? Oh, sorry. Okay. We can see it more easily here. So this is another example of that level-based foraging game. And here is where we would do a central learning reduction of this game, which we can also do with a common reward game. Here, because it's formulated as a general sum game, I am turning this into a normal like Markov decision process problem by instructing it to take, whenever it sees, the rewards assigned to each agent, just take the sum over those. And then that will create a single reward signal. In a common reward game, you wouldn't have to do this. You could just take like the single reward value that would be assigned to all the agents. And then this ends up concatenating the action space together. So here there's like 2 agents, 2 actions. Before, when we look at like a Marl solution, we had those 6x6 matrices. And here instead we have what just looks like a normal action space, but this action space is just 36 actions long because it is representing all of those joint actions, which for the purpose of using a central learning method, it doesn't care about the fact that all these represent joint actions across the 2 agents. And then we just proceed as if we're doing ordinary reinforcement learning, and we try to maximize, in this case, like the sum of the rewards across agents, or this could also easily just be like the first item in the reward signal if all the agents are sharing the same reward. So, if we're applying one of these centralized techniques, or, if we go back and look at like the joint action solution we had for this game, what the book is describing where this becomes like, this doesn't scale well, is that to have a solution like this, we're going to be learning something like some kind of function that goes across this joint action space. And it's really the size of this matrix that becomes the problem. If the number of, like here, there's only 6 actions available for each agent. That could grow, the number of agents could grow. And this then scales like exponentially with the number of agents in the problem. So this space can get very large, and it can just be too impractically big to compute. And also in the book, like you could have a function that just output all of the joint action values. And then actually inspecting that and seeing, well, what is the optimal joint action is trivial, because you have this matrix available as one output of the function. But because this gets too large, the space and the output space might become too large to practically learn. Sometimes these functions, instead of outputting all of the joint action values, they would instead output a single value, but then they would take as an input which joint action you want the output to. So it would output just a single one of these values, and then you would have to then rerun the function with all of these 36 different inputs, and that is also computationally very difficult to just see what the maximizing action is. It may be easier to train other than the computational costs, because you're just training a function with a single output, but so you're kind of stuck whatever you do. But if the action space isn't too big like this, then it is perfectly feasible to just proceed with a problem like this and just do a central learning reduction on it. But we're going to look at techniques where we could apply this kind of technique to the problem because it's small enough, but we want to develop techniques that work at a larger scale, where we're thinking about situations where we have more actions for each agent and more than just 2 agents, and then the action space is going to grow, very rapidly. And this type of, joint action learning is not going to be possible. So here, let me go back to the book here. So that is why we're interested in how can we decompose this value function, which has a very large output space, into something which is much more tractable, and also something that individual agents can compute, where if we deploy these agents, they may not have access to this function that has outputs across the whole joint action space. They may just have access to a function that tells them their own individual action values, like as if they were learning they're the only agent in the problem. And in order to do that, we also need some way of decomposing the joint, because the joint action value function only tells you what to do across the whole joint action space. Like asking the question of what should an individual agent do, is not meaningful, because you have to look at that whole matrix of actions across the 2 agents. So there's this comment here in the book about it being computationally costly to evaluate the joint action space. It's related to what I said, where if your function outputs all the joint actions, this is not true. It's fine. It's easy to look at that. But they're talking about an architecture where you may have, like what they're showing here is the actual action or joint action you're interested in is an input to the function. And in that case, you're talking about a forward pass of the function for every single joint action you're interested in evaluating. And that can get very difficult. So the main method we're going to look at first in this is to look at a linear decomposition of the joint action value function. And we're going to consider, we're going to try to model the joint action value function as something which can be written as the sum of individual functions for each agent. And in this case, they're not going to be like value functions like we're used to, but rather the terminology used in the book is a utility function. Because in the common reward game, the actual total reward is the same across all agents. But when we decompose that, we're looking at trying to model functions that have contributions from each agent to the total reward. And those contributions are numbers that, in this case, are going to add up to the common reward. But the values that we're adding up are not like proper rewards we would normally talk about in a problem, because they are these decomposed values, right, that don't actually exist in the space of the problem. Like in the space of the problem, we just have this single reward value. And yeah, so this notation in the book, this is like the function, like similar to the function I showed earlier, where we have, in theory, this action value function across A, where A is the joint action space of the entire problem. And writing it here, this definition looks exactly like when we have Q functions in ordinary reinforcement learning, where we have this discounted sum of rewards. And actually, the only difference here is what it is conditioned on. Here, it's conditioned not just on, like normally this would be conditioned on the state, and here it's conditioned on these, on the state action pair. Here it's conditioned on this extra information, which is H. This is like the history of observations for the agents. And then Z is like additional information. Like this could be the state information, but normally in multi-agent problems, we do, because things can depend upon the behavior of other agents in the past and their observations, we normally write functions in terms of this joint observation history and not just like the current observation or the current state of the problem. So the idea is that we're going to try to come up with these utility functions, one for each agent, that are only conditioned on the information that would be available to that agent and a set of parameters that are assigned to that agent. And then we want these utility functions to operate such that each agent can look at the action value output of this and then select the greedy action, like just like they would for normal Q learning, where an agent can just look at its own utility function, select the maximizing output or the action. And then in aggregate, when all of the agents do that, then that effective joint action that they get by just maximizing their own utility function matches the optimal joint action value. So that's what's referred to as this individual global max property, which sets up this equivalence here. And the equivalence here is that the true joint action value function has some, maximum, some joint action that maximizes it. And then the individual utility functions, each separately have their own, maximizing action. And the IGM property states that those two things are equivalent. So it's just the statement that this is effectively, like, we don't need this whole, joint action here. We can just use the maximum value, or like the argmax of each of these sub-utility functions, and it will give us the same answer as if we had the true value function. So does that make sense to everyone? What the goal is here? So like we don't have to do this maximization over
So the maximization, or the newer Q function in order to deal with common reward games where the H would be the history, but then the Z will be the hidden state, I think.
Oh no, here Z isn't the hidden state. It's just like extra information you want to include. So
Hmm.
like centralized information. Uh, yeah, like that's the terminology that the book uses.
Yeah. So yeah,
But yeah,
but
the
so far
parameters
that
are.
makes sense.
Yeah, I mean these are just the inputs that capture the current state of the game we're in. If you don't have any central information, this is just missing. So in normal reinforcement learning, this H and Z would be replaced with the current state of the problem. So if we think back to the problem where we had 2 agents, 6 actions each, right? The joint action space was size 36. So we'd have to take the argmax over those 36 joint actions. And here we're reducing it to just 2 argmaxes each over 6 actions. So it's computationally easier to do that. The 36 actions isn't that bad anyway, but you could imagine as this starts getting really large, right? This is just going to scale linearly with a number of agents. And then, this is scaling exponentially as a calculation we have to do. So that is the idea, is we're trying to find a solution that satisfies this IGM property. So the approach we're going to look at today is probably the simplest thing you could think of doing, which is to try to do a linear value decomposition. So the utility functions in this case are going to be functions that we are simply going to take the sum of in order to get the reward. So like these functions should be, if we take whatever the joint action is, we evaluate each utility function at its respective action for that agent and take the sum, that value should equal the true joint action value at that um, joint action A. Right. So like this function in theory could be anything, like the function itself. It can be just any function over these inputs. But here we have, the input is the entire joint action space. So yeah, here this is the goal of trying to learn a function where the actual reward at time t is equal to the sum of the agent utilities at time t, right? Where the agent utilities are the output of their right, of their q. Well, I don't know why this doesn't have a sub I on it, but anytime you see the q function with these I sub indices here, that means like this is just the utility function only depending on the parameters for that one agent, right? Where when it's written like this, then this means it's, some hypothetical joint, however we want to make this joint action value function, but using all of the parameters for all of the agents. So this, this is just a statement of like replacing the joint action value function with its definition, right? And here we have, this is just the discounted sum of rewards, of common rewards. This step, we're just replacing that with what we would like the utility functions to do, which is output a utility value, which when summed is equal to the common reward. And then this is just a rearrangement of this sum a little bit, and it's rearranged in such a way that we just recover the definition we want for the individual utility functions, which is, again, looks like the sum of discounted rewards, but here, instead of the discounted rewards, we have discounted sum of all the utility values they would generate in all of the states right? Like in all of the time steps of the problem. And then the question is whether constructing the utilities like this satisfies that individual global max property that we care about. So there's a proof here. The proof is like pretty easy to follow, I would say. It basically just follows from all these definitions and how the terms expand. But first, are there any questions about what the utility functions represent, how this decomposition works? Good. So remember that the IGM property, it has this if and only if statement, right? So we want both of these things to be true, where if we select the actions according to the individual utilities, that it's the same, that it ends up being the same as selecting all of the actions with the centralized action value function, and vice versa. So this proof first does the proof going in one direction by assuming first that we have what the greedy joint action is with respect to the true joint action value function. And now we have to prove that if this is the case, A star has this property, then the individual actions of all the agents are also greedy with respect to their individual utility functions. Which means that, right, in order for this to be true, for this A star, it means that the value of A star for that agent and its individual utility function must be greater than the value of any of the other actions for its utility function. And they do that here as a proof by contradiction by first assuming that the utility function evaluated at this ideal, what we hope is the ideal action, is actually less than one of the other values here. And so starting from this assumption, which is going to end up resulting in a contradiction, what they do is they just go back to the definition of the utility functions, which is that, we're assuming we have a linear decomposition here, so we can represent this as the sum of these utility functions, right, with the same inputs, right? This is effectively A star. We're just breaking out all the A's into their individual utilities. Then we can separate this out, right, between the sum over all the utilities for the agents where we haven't made this assumption, right? This is saying that for a particular agent I, we're assuming that it is not the actual maximizing value, right? So these are all the agents where it is. And then we have agent I where it is not, right? Or we're assuming that there's some other action, A, that could be the maximizing value. So here, then, we can just replace this and turn this into an inequality where we have now made this term larger by replacing the action here with the action that we're saying is in fact, leads to a higher value, right? And then we have now, right, because we're taking the sum, so now we go back to the definition of the linear decomposition of the value function, where this should be equal to now the true, right, composed, like centralized action value function. But now with this action input, where we have with the optimal action for all of the other agents, the ones that are not I, and then we've replaced the action for agent I with the one that we're saying is better. So now we're saying this is larger than this, but this is a contradiction because we already know that this A star input yields the highest possible output for this function, right? So the proof is very straightforward. It just follows from the definition of how we do the linear decomposition, where we just, replace one of the terms in the decomposition with one that should be higher. And we can see, you know, that actually, if this is in fact A star, it has the highest possible value for this, then it must also mean that all of the individual utilities are also maximized, right? Because if not, we could pick a different one that would yield a higher value to the original function. So does that make sense to everyone? We have linear decomposition, at least in this direction of the proof, that, yeah, having the maximizing joint action also implies we know the individual action inputs that maximize the individual utility functions. So there's also the other direction of the proof, but you know, it's very similar to this one. This one just starts with the assumption that we have the maximizing values for all the individual utility functions, and then we have to prove that that is in fact the same input that would maximize this, you know, Q function. And yeah, this actually just follows more. This isn't a proof by contradiction, but it follows just from the definition of all of these.
So
By showing that,
so basically the proof is basically squeezing it from both sides in order to make sure that the Q policy is the same.
yeah. Well, I mean, the reason why we have to do the proof from both directions is because this individual global max property is a property that states that, yeah, it should go in both directions. That, you know, having, you know, computing the optimal joint action from one set of functions implies the other, and then, you know, so going in both directions works. Just to, yeah, show that these are truly equivalent things, as long as, you know, of course, this is all assuming that we can represent like we make a statement that we have these utility functions where when we take their sum, right, like this, that we recover this function. So like if, you know, like we're just like declaring that this is true. It is possible that whatever this function is, you know, it's not possible to write it down as a sum of functions like this. And then in that case, but if we can, like if this decomposition is in fact possible, then this property holds, where, you know, each individual agent can just maximize their own utility, and we won't lose anything, right? It'll be completely identical if we had actually learned this whole more complicated joint action value function. So we know that if we can learn these functions properly, it will satisfy this property that we need. So now the question is, how do we actually, you know, how do we learn a decomposition like this? So there is a technique. It's called value decomposition networks. Again, it's a gradient technique. Because here we're talking about learning, you know, functions with parameters where we do gradient updates, and we have a loss function. So, you know, in the past, we usually in reinforcement learning we have loss functions that look like this, where we have a target value, which is like a bootstrap target. Where here we're looking at, you know, a function one time step into the future. We have the reward value. So like this would be the loss function for learning the joint action value function, right? This is like the type of loss function we would use. I mean, for the tabular problems, we don't need a loss function because we're just directly taking averages. We don't have gradients, but we're learning this loss function is what you would use to learn, you know, a centralized joint action value function, right? Where we have, yeah, and this is like this bootstrap target. And right, this is the parameters which, without the sub-index, in theory, this is like should cover all of the agents in the problem. But here now we're going to now insert our linear value decomposition into the loss function, right? So we're saying we can represent this function as this sum over these functions. And then, this max term, again, we don't actually have to take the maximization over this because we have this IGM property. We can actually just look at the maximizing value in each of these subfunctions, right? Like normally this is not true, right? Like this is only true because we proved that the IGM property holds. So when we're computing target values, right, all we have to do is look at the individual utility outputs, take their max, and then sum those up. So now if we do they rewrite? I guess they don't write this out differently. But let me go back. So I think in my notes, I have this written out. Okay, yeah. So we have now, like this is the loss function we're working with for these value decomposition networks. Now here this is the target value, y, and if you go back to the book, like this target value, we have to compute this ahead of time. Notice that this, like when we did with independent DQN, where we had these parameters, these target parameters, this is to help with some of the correlation issues with reinforcement learning. But we're gonna, for these target values, keep the parameters fixed for a certain amount of time, right? So the way this works, just like with IDQN, is occasionally we update these theta bar parameters and replace them with the parameters we're learning. But for the purpose of calculating the target value, we're going to treat this as a constant. That's also important. It makes this more of a gradient method instead of a semi-gradient method like we'd have in reinforcement learning, where technically for this to actually work as a gradient loss, we don't take the gradient of the target value, right? Like we need to treat it as a constant value like we would with supervised learning. So here it helps that these parameters actually are not the same as these parameters. They are going to be constant for a certain amount of time. So we can treat this as a target value. So once we compute this target value, then we can write the loss function in what looks like a more familiar loss function, where normally, again, this would be our function of the parameters, but here it is a linear decomposition of that function. Maybe I should make this a little bigger. And right now, this is like a sum of the individual utility functions, each with their own set of parameters. Now, right, if we take the partial derivative of this with respect to just the parameters for a single agent, then we end up by applying the chain rule. We have this term here, which still has this sum, right, over the individual utility functions. And then we have, again, the partial derivative of just the one utility function with parameters I here. So now normally, like you could just like write this loss function out and somehow like you could have it set up where you have this hybrid network where, like, let's say each of these were some like their own neural network. So then with their own set of parameters. So then instead of being like a single network that you could, you have to construct this combined network where we take the sum and then this whole loss function. I mean, that's one way of doing it. If instead we just have something where we can compute the gradient with respect to just one parameter set of values, then we can compute this partial derivative and then we can just multiply it by these values. Now, like, these are all of the outputs for the other networks. So even to compute like one of these gradient passes for a single network, we do need to have this forward pass for all of the other networks available just to compute this delta value. So there's different approaches to it. I mean, in my code, I approached it by computing this sum across all of the networks and computing basically a set of these delta values where we have, right, one, this is over a batch of data. So we have one delta value for each item in the batch. And then also we have these gradient values that we have also for each item in the batch. And we just need to take the sum of these gradients weighted by all of these delta values. But, right, like normally when we do compute a gradient, we compute the gradient with respect to the loss function. So that would just get you all these values, right? It would get you like all of these theta I gradients at once. Here you have to compute the gradient just with respect to this output value. Or, I mean, in this case, it's written as an input value. But, right, if we have our Q give all of the action value outputs, then this is instead like we just care about the loss with respect to that output index. And then with this gradient value, but then when we compute the batch and take this weighted sum, we have to then weight each of our gradient components that we're adding up by this delta value here. But it all depends on exactly what you're using, what's the easiest thing to do. If you can just write down this whole loss function with a sum of multiple networks together and compute the gradient of this whole thing, you could just do that. But considering like these are each independent networks on their own with their own set of inputs here, sometimes it could also be easier to just compute this gradient and then handle this term separately. Yeah, okay. Value composition. So I guess we can see here. I'll show like a little bit of some of the code I have here, but again, like to get the target values, like here. So when we did independent learning in the past, the target values we were using were just related to the reward signal for that individual agent, right? Here we compute the target values like it's shown in the book. They inherently need to be computed over all of the agents, right? So like we have to take all of these individual utility functions together and use that and take, again, we only have to take the maximization over the sub utility function and just its set of action values. But that is what's being done here. For these target values where we have, here's where so for this is for a case of linear approximation where here the parameters for the function are just represented by a matrix. But again, we have n of them where, one for each agent. We get the returns. We compute, here's the part where, so this is looping over all of the individual agents, and then it's getting that maximizing value just for the output of that agent. And then they're being added up here all together with the target value. So I'm going one agent at a time, but then I'm computing the target value for each of the batch elements. And then similarly, these are just different versions of it that use, this is one that uses neural network parameters. But this part of it is still the same, right? We just have to do the forward pass or compute the output values and then take that maximization over the output values. The other step we have to do, right? We have to compute that. We also have to compute this part of it, right? Where this is also going to be that sum again. And this is where the delta value comes in, right? So the delta value is going to be this minus this, where both of these are sums over the individual utility functions. So we also have to compute this on a per example basis. So that's just, this looks very similar again, where we just do, but here the only difference is instead of doing the maximization, we have the forward pass, but then there is the output indices right, relevant to those particular examples. So we're adding the action value from this output for just that, the actual action that was selected. Here, actually might be, so this is their like pseudocode for VDN. Again, we have the computation of the target values, right? These are the loss function here. So I'm showing using the chain rule. First, I'm computing this part in the parentheses here, where again, this is the sum of the utilities at a sub I, where a sub I is actually what's saved in the replay buffer, is the actual action that was selected on this step. So we update the values, and then here, this algorithm actually, so what's being shown here in the book is just this one-step version of it, where the target values are a one-step bootstrap value. What they're using in the book, or for a lot of the graphs and stuff in the book, is probably an n-step version of this, where we want to be able to have more flexibility, where the target value can include more than just one time step. So then you would add up the reward, or yeah, the common reward across more than one time step, and then use this value instead of at k+1 at k plus, some other integer that was however many time steps you're looking into the future. So that's one of the reasons why this code looks a little more complicated. Yeah, where I have this n step argument here. For n equals 0 would be equivalent to the pseudocode in the book, and then n greater than 0 would be, more incorporating more reward values in the bootstrap estimate. But otherwise, the actual structure of this code is very similar to IDQN, just mentioned in the book. The main difference here is just that, again, the loss function is different, where it uses this, combined target value. And then, yeah, like the loss function does depend on the parameters of all the networks in this case because of these delta values. And also the other big difference is that now there's a shared replay buffer where, because of this linking between all the utility functions, when we get examples from the replay buffer, we need to make sure that we're getting the same example for every agent, because we have to add up the utilities across all the agents. If we go back to IDQN, get back here, now we have a replay buffer for each agent. And when we do this training, right, the loss function here and the target value, right, is just dependent on, like, it's truly an independent algorithm where each agent is being trained independently. Notice, like, this loss function, it has no contribution from the other agent parameters. So in this case, when we sample transitions from the replay buffer, it doesn't matter if the transitions match, because each is being handled independently. But for this algorithm, the replay buffer, it has to be shared, and we have, luckily, we do have to worry about having the appropriate, observation for each agent here. But the reward signal is going to be the same across all agents. So that, yeah, like these inputs will differ right here. Like there's no h sub I here. This is saying that the replay buffer, the shared replay buffer, needs to store all of these individual actions and observations, and the subsequent, observation for each sub-agent. Whereas, R, you'll never see R here written with a sub I because, of course, we're in a common reward game. So the reward, value is the same. Yeah, so this is assuming we're dealing with a common reward game. Actually, in my code, I have it, just for convenience, written out to handle a general sum game. But there's this function here, this reducer function. And this is necessary. This is also what you would do with a central learning reduction. But you could sort of turn any game into a common reward game if you have an appropriate reduction function. So here I'm just taking the sum. It's sort of, the game is equivalent whether the agents all get the same reward or like the shared reward is actually the sum, but then each agent just gets that the sum of reward divided by the number of agents. It effectively is the same problem because all the agents share the same reward. It's just that, like this reduction function could also just be taking the first value in a game where it truly is like the same as the common reward situation, where the combined utility function sum is going to equal the reward sum. Here the actual, this ends up being the same algorithm if the common reward they're getting is actually, in this problem, equivalent to the sum of the individual agent rewards in the problem. So you just have to scale the individual agent rewards to be the sum value divided by the number of agents. But by using this reduction function, you can apply this to any common reward game. It might not be appropriate for every game. Like if you have a zero-sum game, this won't work at all because your reduction function is just going to produce a value of 0 on every step, and you can't learn anything from that. So obviously, this algorithm cannot be used for something like zero-sum games, but it can be used for common reward games or games that can be turned into common reward games. Like the agents may get their own separate rewards, but if we take the sum over them, we're just saying that we just care about the collective, success of all the agents together. And that, in principle is the same as a common reward game.
Yeah. So essentially, basically, for a zero-sum game, the reducer function that, is able to account for the common reward function or a generalized reward would just, be a degenerate case then.
Yeah, you would have just R would be 0 for every transition, and you would have no signal to learn from in that case. But that's why we're talking about common reward games. So yeah, this algorithm it does follow the pseudocode. I mean, the main difference here is this function that updates the target values. Here, there's this n step which allows it to handle n step rewards instead of just the single step reward as shown in the pseudocode. But after that, we have this gradient update. Let's see if I update. So I'm just trying to find the code that actually updates this gradient. Oh no, it's down here. So for a linear function, right, this is the gradient update where the parameters are just represented by, a matrix. And this requires this delta value. So remember, I've pre-computed these delta values ahead of time so that when I do the gradient update, like normally, right, it looks like this. To do this gradient update, you need everything here. But again, if you apply the chain rule, you can compute these delta values in the parentheses ahead of time. Then the derivative of the term in the parentheses for just theta sub I, a single agent's set of parameters, right, doesn't depend on the other parameters. So this step here, well, actually, this is but this is just the linear gradient with a feature vector input. Yeah, here. So I've also pre-populated from the replay buffer this feature matrix, which is just a list of all the feature vectors for these examples. And for a linear value function, the gradient with respect to the output is just that feature vector. So this is just going to take the feature vectors, but also it's going to multiply it by the delta values on a per example basis, and then accumulate all of it together into a single batch gradient value. Yeah, where like here we have a batch of some length, and then this factor of 2 is just from the squared error term, where this 2 doesn't really matter because this can just be handled by changing the learning rate, but I just put it here to make it, properly match the gradient value. So this, we can see what this looks like, I guess, on the level-based foraging example. First, I can show. So if we do like independent Q learning, which we had previously looked at, right? This doesn't attempt to learn any value decomposition. This just tries to get each agent to learn its own Q function. And this is for, yeah, linear. So here, these are the parameters of the linear functions learned in this case. You can see it goes this now instead of the state space. This is the dimension of the feature vector. So here, this problem happens with a feature vector of length 132, and then there's the 6 columns corresponds to each of the outputs of the 6 action outputs. And then we have a separate value function, right, for each agent. And yeah, that's it. But of course, this is being trained now on this level-based foraging task where each agent gets its own reward signal. If we instead try to do it with the decomposition, we can do the same sort of thing. The value functions are going to look the same. This is a slightly, yeah, I think I'm showing a slightly different task. So the feature vector is a little smaller, but the output space is the same. We have 2 value functions, and really, like, the output you get is the same as, we have 2 independent value functions, but the difference here is really in how they're trained with the loss function. This is explicitly modeling. This is also doing it as, like, first it's combining the rewards into a sum, and then it's sort of trying to decompose that with the utility functions, as opposed to, independent DQN is a case where we're assuming each agent is getting their own hopefully useful reward signal, and it's learning off of that. But of course, IDQN is not, it doesn't actually, it's not guaranteed to converge to anything. Training IDQN is not equivalent to solving the single agent RL problem across the joint action space. This actually is equivalent to doing that if the linear decomposition works, because we have this single reward signal that we're using. And because the level-based foraging game is a cooperative game, taking the sum over rewards, makes it a proper common reward game. But again, like, this is a full stochastic game. There's a lot of states. What the book does after this, which I think is very useful to look at, is it uses these matrix games as a sort of a test case example where we can see very clearly what is going on. And this is helpful because we can sort of take any matrix game and, like, stochastic games are a superset of matrix games. Like, we can take a matrix game, turn it into a stochastic game where if it's a non-repeated game, it just means that this is a game where we have 2 agents, 2 actions, right? A and B. And then this is like the playable game state. And these are the rewards for each of the joint actions. The common reward in this case. Okay? So, and then after this, the game ends. Another way of saying that is it transitions into a terminal state where there are no more rewards. So we can actually use all these algorithms like VDN and IDQN on a game like this. Of course, it's overkill, right? This is clearly, we're in the realm of tabular games here, right? We don't need to use a gradient method to solve this game, but it is a good way to illustrate what's happening with the algorithms, and also, how, if we've written them correctly. So the first game example they have here is one where this can be decomposed into 2 utility functions. They have an example of one of the decompositions here. So you imagine we have first our function for agent 1, and it has a value of 1 here for action A. Oh, I guess it would be on this axis. And then 5 here. And then for this agent, for action A, it has a utility of 0, and for action B, a utility of 4. And you can see, like, these are the true values. And if you go through each of the combinations, like AA, we can see if we add A and A, we get 1. Right? If we add A and B, we get 5. Same here. And then if we add B and B, we get 9. So this is one of what is, an infinite number of these proper linear decompositions of this value function. And then they have an example here of training VDN on this, and it learned a slightly different decomposition, but yet one where it still reproduces the proper joint action value function, right? So the important part of this is like, let's say we were, well, actually, let me go back to the notebook, because so I did set up these examples in here, these matrix games, and we can see like a few more other things we can do with the matrix games. So, right, this is like the first game, we're just dealing with 2 actions, 2 agents, 2 actions. So here's the reward matrix, right, as it was defined in the book. Now we can turn it into a tabular matrix game, which, it is, because it's a very small action space. So here, to see what's really going on with these algorithms, to make this a non-repeated game, which is important, right? If it's a repeated game, then the values end up being different because, you're going to get reward into the future. But when you write a matrix game like that, you're saying like, these are the rewards you get after the action selection. And that's it. There's no future rewards. The game is over after one step. So that's why you kind of have to structure it where there's a play state and a terminal state. The play state is the one with these reward values. And here, right, we have 2 agents, 2 actions. Here we could see the whole transition function. It's very trivial in this case, but this just means all these 2s. It just means that after an action selection, you're always in state 2, which is the terminal state, because it's a non-repeated game. Then we have the reward transitions in here. These rewards, to make this work the way I've written the algorithm, I'm actually turning this into a general sum game, right? So each agent gets its own reward, but the values are or should be equal. This, like the way I've created this game, I'm taking the reward matrix, dividing it by 2, and then just assigning that that same exact reward matrix to each agent. But I'm dividing it by 2 because when I do VDN later, I'm going to take the sum of the agent rewards, right? So it's going to be equivalent to the common reward case. Yeah. Okay. That should be it. Oh, I think it's confusing here because the way this is being broken out is a little confusing because it's not for each agent. But basically, each agent's reward matrix should just be this divided by 2. So it should be 0.5 and then 2.5 here on the corners, and then 4.5 for this action selection. Okay. Now again, these common reward games, they are equivalent to MDPs, right? There's a single reward value. So I also can convert this into an MDP here, again, by taking the sum. It's the same reduction function I would use for the value decomposition network. But now I've started out with this, reward matrix. Now I've turned it into now what is effectively just a normal reinforcement learning problem, where now, the action space, again, this is the thing that's going to blow up exponentially when we have more agents and more actions. Now it is a very, easy to handle 4. So, right, these are just the 4 joint actions, which correspond here to these 4 different values here. And then, yeah, here's the transition matrix. We have now a single reward value because we're not even considering the 2 agents anymore. So, and then, we can also turn, in order to test VDN and all these other things, I need to also have a version of the game which is not tabular, where now the state information is obscured. The only really difference here is now, I don't have the states anymore, and I have to actually represent this as yeah, so like the actual state type in this case is a symbol because I have these two symbols. One is play and one is term. So that's just what this symbol means, is that this is a problem where the states are symbols. In this case, there's just two of them, but right, this type is designed to handle games where we don't actually know ahead of time how many states are in the game. This is just for testing purposes. Obviously, like you would never try to solve a game like this with any of these techniques because it's overkill. But we could see, so if we solve this with, a normal reinforcement learning technique like value iteration, right? We can just get, I mean, we can solve like this is a completely trivial problem because we know what these values are, right? There's just four values, 1, 5, 5, 9. They match the values in the reward matrix. And of course, a technique like this can find out what those are. So here I'm writing it out. I'm rewriting it as joint action values in this matrix again. So of course, like if you're actually trying to learn the joint action values, here's what we've learned. Like the actual, true joint action values. Fine. So this is the exact solution. Again, it's a good test. It's verifying that our value iteration is actually correct because, right, in order for it to be correct, it has to be able to reproduce this matrix here for the reward values. So it's a good confirmation. Everything's working. The conversion from a multi-agent problem to a single agent problem is correct. And then, the representation of the joint action values is correct. Okay. So now we can look at the actual multi-agent techniques. So they don't do all these matrix games like this in the book, but just for completeness, I'm going to show more than just the value decomposition techniques. So first, let's look at independent Q learning, where again, this is a tabular method, right? The way we update the Q values here is by taking averages rather than gradients. But again, this is using like the actual value estimate we're learning here, because this is a tabular technique, is just these matrix of values. What's being shown here, ignore the second column. This is for the terminal state. So it's learning, each agent is learning, its reward value, right? Again, the reward each agent gets here is going to be the 1/2 of the total, because then I'm going to take the sum afterwards. So here I'm actually training independent Q learning, but it's the same as learning the utility functions, right? Because the utility function is supposed to sum to be the reward function. So here, this independent Q learning is not trying to learn like a decomposition. It's just learning each agent's actions, rewards independently. But in this case, because of the structure of the matrix game, it is able to learn, like the values it should learn here are 2.5, and 4.5, right? Because then if you sum the 2.5, you end up getting 5. And then if you sum the 4.5, you get 9. Of course, by doing that, you don't get the correct value. You do end up with this first value here is the lowest value, but it's not actually the correct value. Like to be correct, also I'm training this with this value of epsilon for exploration. And because the values it learns actually depend on the states visited in this case. If I change the value of epsilon here, it ends up, right, it lowered, yeah, it ends up lowering this value. Here, flip this back. Again, whenever you do these value function techniques, you need to have a way of exploring the whole state and action space. And because we do these averages, depending on what the technique is, because like we're not actually learning this joint action value function, right? I am adding this up after the fact. What's actually being learned here is the individual value functions here. And because these aren't joint action values, the individual value functions are affected by the value of epsilon. Even though if we actually learned like we do in value iteration, where we're actually explicitly learning these 4 different values, joint action. I mean, here, the space of the individual values, right? We have 2 and 2. That's actually the same as 2 times 2. So the space is the same size because this is a test problem. But we'll see later. If we had like 3 by 3, let's say, then we'd have, 3 values for one agent, 3 values for the other, but we'd have 9 values for the joint action value function. But here, we do end up recovering. So like if both agents follow the greedy policy here, they would each select action 2, which is in fact the correct thing here. It's being shown here, right? Clearly the optimal action for both agents here. Like in a common reward game, there's no conflict between the agents. So here they both should select B to get this value of 9. And that's what, if we learn the true optimal policy, it should be equal to 9. Here with independent Q learning, we're not actually learning the correct values here, but we at least are learning this correct, optimal policy. Now, instead, we also had a tabular technique that did explicitly learn joint action values, right? For each agent, that's what's being shown here. And this has no problem. It learns the exact value function because we are explicitly learning, right? This is the thing we're trying to avoid with the decomposition methods. We don't want to actually have to learn all of the joint action values. But because this technique is learning them, it is just as accurate as something like value iteration, right? It is able to separate, right? There's a separate estimate for each joint action value. So right here, like I'm not even showing the 2 like utility values because they don't exist with this technique. This technique and also what else is nice about this technique is that if I make epsilon 1, which means that during training, these agents are just following completely random actions, it doesn't affect the learned values here. Just like, with Q learning and reinforcement learning, if we're actually learning, Q learning in theory should be able to learn the optimal policy, even if we're exploring randomly, because it's an off policy method. This is similar with learning all the joint action values. We can crank up this epsilon to explore everything. Of course, this is only working because this game has one state, basically. So we're just learning, the correct action values for this one state. This would not be the same situation if this is a true stochastic game, because then this epsilon of 1 is going to affect how frequently we visit different states, which can then in turn affect the value estimates. But, for this case where we just have one state, this is robust to changes in epsilon, and it learns the exact values. And then the policy, this is not actually the greedy policy, but rather the empirical policy learned during training. Because here, right, this is a technique that tries to model the policies of each agent. So here, this is the policy it's learned for each agent. But this is just related to epsilon, right? This is just reflecting how often we explore random actions, right? It's about 1% of the time. It's a little less than 1% because the random action could also be action 2. But you'll see if I make this like 50%, the empirical policy is going to, get more random because now it's following the greedy action half the time, and the other half of the time it's choosing randomly between 1 and 2. Okay, so these are the tabular techniques. Now let's look at the gradient techniques we're looking at in this chapter. In order to use this, we have to create a feature vector. Here it's a trivial feature vector. I'm just basically using a one-hot vector where the only reason I even need a one-hot vector is because there are 2 states, right? There's the place state and the terminal state. So this will just be the only one we care about is the vector 1, 0, where 1, 0 just means we are in that one state, and then those are the parameters that will actually be trained. So this is doing IDQN, right? This is like the gradient equivalent to the independent Q learning I showed earlier. So this should have the same sort of problems we had with independent Q learning, where it is learning the correct policy, right, of action 2, but the value decomposition is not, quite right. And again, like it is affected by this value of epsilon. Like here, I make this 1%. Now the values are actually closer to what the true value should be, right? Like in the true problem, this should be 1,559. So now this is closer if I reduce the exploration. Because, again, there's nothing about this which is explicitly forcing the individual utility functions to, to be the sum, the correct, to sum together to be the common reward. I repeated this a few times just to check all the different techniques. So this is using linear approximation with a different way of representing the feature vector. And then this is with a nonlinear representation. But again, like the nonlinear function here is irrelevant. Like this is a trivial problem. It's just a way of checking that all the gradients are working properly. We can see this is basically working, right? It's getting this optimal policy for all of these situations. So now, finally, we'll get to the VDN solution. Where here, this is, again, it's learning two value functions, right? Two sets of parameters, just like before. And now, you can see even with this epsilon value of 1, all right, which means it's just following random behavior the whole time. This gradient method, even though it's not explicitly learning the joint action value function, it is learning this correct decomposition where it's getting these values of 1,559, and then these are the actual values it's learning, right? A point. So it learned this decomposition of about 0.5 and 4.5, right? And that is one way of accomplishing this, right? Because if you add up 0.5, you get 1. If you add 0.5 to 4.5, you get 5. And then if you add up 4.5, you get 9. So this is like a proper decomposition of the joint action value function. We can see this worked for all of the different feature vector representations and for the nonlinear function as well. So yeah, that's why like the difference between this and the IDQN is, or the independent Q learning, is the independent Q learning. It's working, like it's getting the optimal policy, but we could see it's not getting the correct values, even though there is a correct way to decompose these values. And, again, each time we do a gradient update here, we're using all that shared information because we're also using the value function output of the other agents as well. So this learning is probably more stable for that reason. But again, like this is only suitable, right, for the common reward games, or a game where we can apply that reduction function to the reward signal. So any questions about this or the success of the VDN on this problem? Okay, so there's this other matrix game example is a little different. So for the first one, it had a valid linear decomposition, right? Where we could actually represent it as that sum, like, right? Here's the decomposition, right? 0.5 and 4.5 for each agent is a proper decomposition. Now, this matrix game, this is what the reward matrix is. The values are all 0 except for a value of 10 for the joint action of, right, both selecting the second joint action. Now, this matrix doesn't have a linear decomposition of the utility function. Like you can't write down a function, and there's like a little diagram in the book here of what this surface looks like. So this is an example of, like, let's say, you basically need a function that gives you a proper output. Like the actual joint action value function has to be a function in this space, right across in this like two-dimensional input space. And because of these 4 zeros, it clearly doesn't have a shape where you could like draw a plane in the space and hit all the points, which is the case like for this first example we looked at. We can draw a plane. Like you could see the symmetrical nature with the 5s. Like you could draw a plane through this space, this surface, and that means you could do a linear decomposition of this function. This one, on the other hand, does not have a linear decomposition that works. So there are additional problems with this. Now, if we train it like the exact solution, it should work the same, right? If we're learning the joint action values, we can learn these exact joint action values because, again, there's no issue with the decomposition here. Now, if we do independent Q learning, where we're not explicitly learning any decomposition, we can see here that it is getting like the ranking of the between the actions is correct here, right? Like this action of 2, is the optimal action. We can see if we sum the individual value functions, again, we're constructing the joint action value function as a linear combination of these 2 value functions. And we can see that it's doing something, but this is like the best it can do, is that it can't make these 2 values equivalent, right? Because these 2 values have to be used to sum to the value of 10, which means that the values in the corner are always going to be non-zero. So it can't learn the true value function here. We could see also this is affected by the value of epsilon. If I make this higher, it just changes the balance of the error function, because here it's not mixing more of the value from the 0 reward into this estimate. And same here. If we go back to a lower value of epsilon, it's following this action more frequently. So it's not, the averaging is not including the 0 reward you get for these mixed actions. If we do the joint action learning like we did before, again, it works fine. We don't have any issue because we're explicitly modeling each joint action value separately. But, IDQN, again, this is like just checking for completeness that this is working. This should basically produce the same output we got for the independent Q learning, and it does, right, where we're not able to get these zeros. And we have the same problem, right, with value decomposition networks. Now, it does learn a different decomposition right here, and this is also now affected by epsilon somewhat, because we can't actually get the exact, there is no linear decomposition for this matrix. So here, if I like change this value of epsilon, I'll put it way down. One, like we're getting a decomposition where we're getting now a pretty accurate value for this because it does happen to produce the correct policy here. But, if I make the exploration larger, this value is going to drop. I mean, again, we have the problem where we can't make all 3 of these values equal each other, which for this game doesn't matter that much, because really what we care about is knowing that this joint action value is the best one. But we clearly don't have an accurate value function representation. Like and because of the lack of a linear decomposition, this technique doesn't really do any better than the independent Q learning, right? I mean, either way, we have a value here which doesn't match these values here. And then the value in the corner is probably going to be too low of an estimate. Now in the book, we're not going to get to it this time, but there is this other technique. This QMIX technique basically does a decomposition in a more flexible way. It doesn't only do linear decomposition. And for this game, this algorithm can learn this decomposition properly because it is a monotonic game. Monotonic because if you increase the utility of any one agent, it also means that the overall reward is higher. So this is suitable for representing any monotonic game. But we can see that this and VDN and everything else will again struggle with non-monotonic games like this one, right? So this is a game where, we have rapid changes to the reward signal depending on changing the action, and we have, actually in this two different Nash equilibrium solutions here as well. But we could see with neither technique is able to learn. I mean, also the optimal action here is AA or 1-1. And not only do these techniques fail to get the correct value function, they also fail to learn the correct joint action value. And that's part of the reason for that is because you can see the shape of this function, right? This optimal value of 11 is if you deviate from it, from any agent, you get the worst possible value in the game. So clearly this is highly non-monotonic, which is why this technique's failing. It also doesn't have a linear decomposition. So for this, we would need a totally different, decomposition technique. And if you look at the chapter, some of the techniques recommended involve using functions that effectively have outputs over the joint action values. But again, if we're going to learn functions over the joint action values, we can already do that. Like, show here. So this is the climbing game. Right now, doesn't have any of the nice properties we were relying on earlier. We can still, of course, get an exact solution, right? If we actually learn all the joint action values, no problem. Same with, independent Q learning is going to fail in the same way. It thinks that the optimal action is this one in the corner here, which is this. Clearly not, there's a better one here. There's a better one here, but, this happens to be, you can see if we're doing monotonic or linear combination, like because this is in the proximity of other non-negative values, it ends up looking better just because of the structure of the reward matrix. So these are the again, all this technique can do is learn individual action values. So it learned these values, and then this is what they sum to, which is clearly not the correct values. But if we do joint action learning, again, a technique from the first half of the book, it has no problem learning the exact value function here. We already know, this is a solvable problem, actually learning the action values. And then if we go to so here, this is my VDN solution. See how it compares to the one in the book. It's like negative for, it also, the VDN solution also thinks that this joint action value is the optimal one. It's like 3 and 5 point something. Yeah. So it roughly matches what's in the book, but it does end up learning this, attempts to learn this linear function, which just cannot fit this reward matrix. And the best it can do is to think that this action is the best. Let me just see. Yeah. They also train this on a version of level-based foraging, which is a common reward version of the game. You could also get that by taking the sum of the rewards, like I did across the agents. And here they're claiming that, QMIX has a better performance than VDN or independent DQN. Maybe we'll probably save talking about QMIX a little more for the next meeting. But, even though QMIX is better, like clearly there are these examples you can come up with, like this one, where we have a game with monotonic rewards, then QMIX is ideal for this. It'll work. It'll be better than VDN that will fail. Also, if you have like these multi-state games here they've combined the two games into a stochastic game, where depending on the action selection here, the agents will either transition to playing this game or this game. Now, we know that it's better for both agents to play this game because the optimal joint action value gives a reward of 10 to both agents. And here it's only 9. But we can see with the VDN solution, because the VDN, even though for this non-repeated game, we saw here, it knows that this is the optimal joint action, right? Even though it's not a proper linear decomposition, this is correct. However, the value is wrong, right? The value is being depressed because it's trying to balance the error in these states and this. Now here, because this is linearly decomposable, these values are correct. So even though the action selection here is correct for this game, now because this is a multi-step problem, starting from this state, VDN thinks that this is not as good as this because the optimal joint action value is lower, because this value is incorrect. It should be 10. Here, QMIX learns correctly that it's 10. So this is a case where even if in a simple, like a matrix game, you get the correct, ranking of the joint actions, if the values themselves are too far off, you can wind up with issues like this where you don't transition into the correct state because the values are wrong. However, both of these techniques will fail with more complicated games. And the main problem is that if we have a game that we're trying to model, we don't know ahead of time what the states are going to look like. If they're going to have like non-monotonic behavior like this. So because of that, we don't know ahead of time which of these techniques is going to be suitable. And we couldn't, at that point, we may need to use, here's beyond monotonic value decomposition. So there's more elaborate things you can do. This is now a technique, another technique where you end up learning a centralized action value function in this technique. Of course, we could just try to solve the problem with a centralized action value function, like treat it as an equivalent MDP. And considering how complicated this is, it's true we have a problem with the joint action space getting large, but this has the same scaling problem with the joint action space. So if you really have a poorly behaved problem like this, it may be better to just, bite the bullet and try to learn all the joint action values, which won't have any of these problems. If we know ahead of time that, it's going to be linearly decomposable or monotonic, then these techniques will work well in those cases. But otherwise, we're going to have problems. There's other convergence problems with this technique, but I'd say the main problem with it is that whenever you see this, if we have to learn it, it's true, this is only used for training. So this may be good for a situation where the agents have to be deployed with their own individual utility functions. If we truly use a technique that learns the joint action value function, each agent would need access to that in order to operate in the environment. But you could also just disseminate the full joint action value function to the agents or share information with them. Yeah. Okay. I think that basically is all I wanted to say about this for now. Maybe next time we'll probably move on to the 9.6, but we may touch a little bit on how QMIX works, because it is kind of interesting despite the shortcomings. Like here we were looking at VDN where we have these individual neural networks with utility functions and we take the sum of them to represent the full one. QMIX is just an extension of this where we just combine the individual network outputs with another neural network, which in theory you could represent any decomposition. But the problem is, in order to meet the IGM property, which is necessary for this to work, this has to be a monotonic function, this mixing function, which we can certainly do. But again, it means that this technique can only model value decomposition for things that have a monotonic value decomposition, which sounds like it's a lot more capable than this, which requires there be a linear value decomposition. But I don't know, practically across problems you're actually interested in, I don't know how often you get, these monotonic decompositions. Like it may be, I'm guessing it's a problem because there's all these other techniques people have tried to come up with to relax this monotonic constraint, but they all have their drawbacks, like needing to deal with the joint action space again, which is the whole reason why we started doing this in the first place, was to avoid explicitly trying to model the joint action space. So next time we will start looking at some techniques, other ways of avoiding the joint action space with this. Yeah. So we looked at agent modeling in the tabular case. That's actually what I showed in this notebook. Right. These solutions that actually learn the correct joint action values do so in part with using agent modeling as well. So perhaps, these techniques will be more suitable for more complicated matrix games like this. But are there any questions about anything I talked about today? Or anything anyone would like to see again on the screen? Good. This was the agent modeling. So we looked at this in part 1 of the book, agent modeling with tabular problems. So next time we'll start getting in a little bit to how agent modeling works in the case of approximation and using like neural networks to model other agents' behavior. Yeah, so I think for next time we will, maybe I'll touch a little on QMIX just to discuss like how you'd actually compute these gradients. Again, like the gradient is already like, you have to handle this sum of networks. Here you need to then sort of pass gradients back through a mixing network, and then, so, this type of technique might be useful later. This monotonic function. So what I was showing here, basically, like in these matrix games, because these only have one state, like these are the correct joint action values. So with modeling, we're trying to learn a decomposition where we just like have these two separate functions, right, of two different values. So the true values, like these 4 values could be anything. And depending on what they are, it either is decomposable with a monotonic function or not. So like this does have a monotonic decomposition. This doesn't. The book doesn't like prove that or anything. So that's like the thing you're actually trying to model may or may not have a monotonic decomposition. But yeah, that depends on the true values. Now, to ensure that the function, like our modeling function, is monotonic, that requires we put constraints on the actual function that we are training. And in the case of this, these utility functions could be anything. They could be just any neural network function. For this to be monotonic, basically this mixing function has to be monotonic, meaning that if there's an increase in one of these input values, it has to produce an increase in the output value here, right? I mean, it's monotonic in each of the utility functions, is this output function. So in order to make sure this is monotonic, there's one way of doing it. One simple way of doing it is just to make sure that all of these mixing parameters are positive. And that ensures that this is monotonic. As long as our activation functions don't I mean, the activation function should also be monotonic, which usually they are. I don't think it's pretty unusual to use non-monotonic activation functions in a neural network. It doesn't have to be strictly monotonic either. Yeah, like that. So practically, also the way this is done, we don't worry about values being zero. Like if like strictly monotonic means that, right, like an increase in one value should always produce an increase in the output. We also will allow the output to stay the same value, which isn't strictly monotonic, but practically it's all we can do. Because like one way of doing it is to use an absolute value function on these. And if these values are zero, then the absolute value won't make them positive. So, but that's usually what's done here. So it's not strictly monotonic, but it's, weakly or well, whatever the term is for relaxing that to not relaxing the greater than sign to be greater than or equal to. Wait, is GELU is actually is that actually non-monotonic, or is it? I thought it's just it's flat in a section, but if it's actually not monotonic, then you wouldn't be able to use it in the mixing function. You could use it in each of the utility functions. That would be fine, but mixing function should only use monotonic activation functions and strictly positive or zero mixing parameters here. But yeah, this is a little bit of a convoluted architecture. Like basically, you have this mixing function. You use another network to produce the parameters you use in the mixing function, and then you have to train the gradient through this whole thing, which is a little convoluted. Also, again, like this is restricted to only work with monotonic decompositions, which is also you're going through all this trouble, but then you're still stuck with that. So, I don't know. Like this comparatively is much more straightforward to deal with. And of course, both of these techniques can fail if the true Q function is wrong. But yeah, so there's some interesting things with the gradients and QMIX, but otherwise we'll move on to 9.6, which deals with agent modeling. And yeah, joint. So this basically is the deep learning equivalent of this, right? Where we already did joint action learning with agent modeling in the tabular case. And this has a lot of advantages. It can work well, although we do need to learn. I mean, we spent all this time explaining how we want to avoid learning joint action values, but then, we're going to end up doing it anyway. So perhaps the joint action space is not too big to be a problem. But yeah, I believe this whole subject will be just the gradient method equivalent of what we did before with joint action learning and agent modeling. So yeah, we're just going to go back and ignore all of the caveats we said about how we shouldn't learn joint action values. Also, it's important to learn joint action values to do anything more complicated with equilibrium solutions, which is also what we need to solve any general sum game. So I believe that we're going to have to go into that anyway. Yeah, so we'll try to cover as much of 9.6 as we can get through, but possibly the whole thing. So any other questions? Okay, well, if not, thanks for coming, everyone, and I'll see you next time.